The issue we want to talk about today is how to use the correlated uniform distributions in SIPmath. To do this, I'm going to go through an example where we've been given some historical data that represents the cost of a new platform and the cost of steel. And that historical data is shown over here. And we have 100 samples from that we've collected historically, and we've plotted that data. Then our procurement organization has assessed the possible range of steel index in the future, and that is indicated below. So it's indicated as a triangular distribution with a minimum, most likely, and max. Basically, that's how they've assessed it. And then the facilities engineering department has assessed the platform cost as $750, $900, and $1,500. And this is in dollars. So our task is to generate a distribution of the facility costs and show it in a scatter diagram against the steel cost. So let's look at the process, the evaluation process. What we want to do is determine the correlation of the historical data. Then we're going to generate a correlation matrix of the uniform variables. Then we'll use the SIPmath toolbar to generate two correlated uniform distributions. And then generate the correlated triangular distributions using those correlated uniforms that we calculated in step 3. So what's the random variables in step 3 really represent user inputs as far as the triangular distributions are considered. Now that we have our estimated platform costs and steel index, we can define those as outputs and then plot them as XYs. We then can use the SIPmath toolbar to generate a cumulative distribution of each and or a histogram. As an alternative, we can calculate the percentiles for each of those variables and plot the cumulative distribution. So let's get started. Over here in the historical data, we've shown the 100 historical data points, and I've calculated the mean and the standard deviation for each of those variables, and then the correlation. The correlation turns out to be 0.753 historically. So the next step was to generate a correlation matrix, and that is shown over here. So this is the correlation between steel and the platform. I guess I calculated over here as well. Okay. We now want to generate correlated uniform distributions. So we'll do that over here. This is the correlated uniforms. So what we'll do is we'll highlight those two cells. If they're going to be correlated, there always has to be two or more variables you're doing. Go to SIPmath toolbars, generate input. We're going to correlated distributions uniform, and it asks for the correlation matrix. So our correlation matrix is right here. It wants an external random variable. I'm going to put that right here. And we'll just use the HDR with the starting variable with no seed. We hit OK. What I didn't do was initialize the model. Let's see if we can do that at this point in time. SIPmath tools, initialize, and I'm going to go to 1000 simulations, and there we have an answer. Very good. So these are correlated uniforms. These are going to be uncorrelated uniforms. We'll wrap those and make them smaller. We now want to generate our correlated triangular distributions. So we will use these correlated uniforms as a user random variable. So over here, we'll highlight these two, SIP-Math Tools, Generate Input, and these are going to be triangular. The minimum is going to be here. The maximum most likely here. And the maximum here. The external random number, let's see, we're going to use a user, is going to be right here. Here are these correlated uniforms. Those are our user data. And we'll say OK. I now contend we have generated triangular distributions for steel and platform costs that are correlated. We now need to generate our outputs. So let's call this D underscore steel index and D underscore platform cost. Highlight those, and we'll go to SIP-Math, define outputs, and output names are here. Let's okay, we'll do some, and then what we can do is we'll just make these a bit bigger so we can see the distributions. So indeed, the platform cost is a triangular that's asymmetric, and the steel index appears to be triangular, somewhat symmetrical. So now what do we want to do? We want to plot the cross plot of these two things. We're going to come over here to the PM index, PM table, and we will do a cross plot. I'm going to put the platform on the y-axis, so Shift N down, insert XY, and then we'll edit this, design, select data, edit, and we give the y values, and the y values are going to be the or the x values are going to be the steel cost. All right. Okay. So there we have our results, and this will look a lot better if I format this data series, and I always have trouble getting the right things here. So we go to fill in line, we're going to go marker options, we'll do built in, and we'll change this to 2 point size. And then I can come down here and change this to a 300, I think, looks like. And maybe change this to 600. And now we have a pretty good chart. And it shows 1,000 simulations of the axis titles, and this was steel index, and this was the platform cost. We then wanted to generate a cumulative distribution function for the platform cost, so we'll come over here and go to SIP-Math, graphs, and we wanted a cumulative distribution function. So there we have the cumulative distribution function for the platform. Now in our evaluation process, I have suggested there's an alternative of calculating the percentiles. Let me show you how to do that. So I'm just going to generate a new sheet and call this CumProb. And then we'll come over here and we'll start off with 0.002, just to pick up the low end, 0.01, 0.02, and then let's just copy that down a ways, like 100 things. And then this last one we'll put 0.998. Up here we'll put the percentile of our array of the platform cost. And I needed to add the percentile here. And I'll copy that down. And now I can plot this as an XY. This is our percentile, and this is the platform cost. So we'll click that, insert an XY, This chart's pretty good, except I'd like to change the chart type. Now we're looking good. And we'll do one more thing. We'll give this a value of 600. And we'll bring that over to our model page, Control X, model, and we'll paste it right down here, right below this one. And then we can compare those two charts. So I think we've accomplished our objective. We now have 1,000 samples that are consistent with our subject matter expert inputs with a correlation of 0.75 based on the historical data. And we can utilize that in our model that may include other uncertainties.